Welcome back to the Explainer. Today, we are exploring an absolute paradigm shift in machine learning. For the longest time, the entire focus of the field was on finding this perfect algorithm, this mythical lone hero model that could just magically solve any problem you threw at it. But what if we completely stopped searching for a flawless individual and instead focused on building a powerhouse team? Well, that is the core concept behind ensemble methods. We're going to see exactly how combining multiple imperfect models leads to incredibly powerful, accurate, and robust predictions. Okay, let's dive into this. Here's our roadmap for the squads we're building today. We'll start with the weak learner theorem, move right into bagging and variance, and then tackle boosting and bias. After that, we'll level up to stacking and meta-learning before finishing the whole thing off with an actionable production stack playbook. Before we get into the specific techniques, I want you to consider this quote. A group of weak learners combined correctly becomes a strong learner. Now, listen closely to this next part. This is not a metaphor. It is a mathematical theorem. The magic of ensemble methods isn't just some clever analogy about the power of teamwork. It's a mathematical certainty that actually underpins most modern production-grade machine learning systems. So, Section 1, the weak learner theorem and the power of diversity. To really build our ultimate machine learning team, we first need to understand the fatal flaws of working alone. Think about the models you might use completely on their own. A single decision tree, sure. It's fast, it's highly interpretable, but it's also incredibly hyperreactive. It learns the background noise in your training data so well that it completely overfits and just fails on new data. On the total opposite end of the spectrum, a single linear model is overly simplistic. It draws a rigid, straight line and completely underfits complex boundaries. Now, you could spend days or even weeks trying to engineer the absolute perfect, infinitely complex architecture. Or you could literally just combine a bunch of imperfect models and get an output that is vastly superior to any of them individually. The math behind this is just stunning. Imagine a classifier that is basically a C- student. We're talking barely better than a coin flip, sitting at maybe 60% accuracy. If you take 101 of these independent, incredibly mediocre classifiers and you let them take a majority vote, their collective accuracy skyrockets to 84%. How is that even possible? Well, because when they're independent, their errors actually cancel each other out. They don't all make the exact same mistakes at the exact same time. But this requires diversity. If all 101 models are perfectly identical, your accuracy just stays stuck at 60%. But if you force them to look at the data differently, the ensemble becomes a genius. Moving to Section 2, bagging and variance, or what I like to call the parallel squad. So how exactly do we force this diversity when our models are just overreacting to data and memorizing noise? So the crucial point is we use a technique called bootstrap aggregating, or bagging for short. Bagging creates diversity by training each model in parallel on a completely different, random subset of your training data drawn with replacement. Because every single model sees a slightly different version of the world, they all develop different biases. A really famous example of this is random forests. It actually takes this a step further by not just randomizing the data rows, but also randomizing the features, the columns, considered at each split. When you average all these highly diverse, noisy trees together, the noise just smooths right out, drastically reducing the overall variance of your model. And here's a brilliant built-in freebie of the bagging process. When you randomly draw data with replacement to build your bootstrap sample, statistically speaking, about 36.8% of your original data gets left out of that specific draw. We call these the out-of-bag samples. Because the model being trained literally never saw this 36.8% of the data, you can actually use it to test the model's accuracy. It serves as a totally free validation set. It literally saves data scientists from having to carve out and sacrifice a separate holdout set from their precious training data. All right, Section 3, boosting and bias. Meet the sequential fixers. If bagging was all about calming down overreactive models, this next squad takes the exact opposite approach. We're shifting our focus from variance to bias and from parallel teamwork to a strict sequential chain of command. And this brilliantly illustrates the fundamental difference in architecture here. With bagging, it works in parallel. It targets high variance, and it relies heavily on random subsets. But boosting, it works sequentially. It targets high bias, meaning it fixes models that are too simple to begin with, and it operates by deliberately, mathematically correcting the errors of the models that came right before it. Let's walk through the evolutionary steps of boosting. We start with a base learner, which is often a decision stump. That's literally just a tiny tree with one single split. It's incredibly weak. Well, the next evolution of this was AdaBoost, or adaptive boosting. AdaBoost trains a stump, looks at exactly what it got wrong, and literally increases the mathematical weight of those misclassified samples. So the next stump in the sequence is forced to pay way more attention to those harder, highly weighted examples. Finally, we evolve to gradient boosting. Instead of just changing sample weights, gradient boosting mathematically calculates the exact errors, the residuals, of the previous model, and then trains the new model to predict those exact errors. It literally fits the mistakes of its predecessor. Which brings us to the absolute ultimate Kaggle weapon, XGBoost, or extreme gradient boosting. Why does this thing win so many competitions? Because it's gradient boosting on pure engineering steroids. We're talking strict L1 and L2 penalties, so individual trees don't get too arrogant. We've got second-order derivatives for much smarter splitting decisions, sparsity-aware splits that just natively handle missing values. It even optimizes its own memory layout to run at blinding speeds directly on your CPU cache. It seamlessly combines statistical brilliance with raw, hyper-optimized systems engineering. Section 4. Stacking and meta-learning. Think of this as routing to the experts. What if we want to combine totally different types of models entirely? Think of this next technique like hiring a brilliant manager who knows exactly which team member to trust for a highly specific task. This is stacking, or meta-learning. Instead of just vaguely averaging predictions out, stacking actually uses the outputs of your base models as the input features for a brand new overlying model, the meta-learner. If your random forest is really great at handling certain data regions, but your support vector machine absolutely crushes it at others, the meta-learner dynamically learns this and routes the trust accordingly. But a massive warning here, data leakage is a huge danger. You absolutely cannot train your base models and generate your meta features on the exact same data. If you do, the meta-learner will simply learn to blindly trust whichever base model overfit the data the most. You have to generate these predictions using strict cross-validation. Finally, Section 5, the production stack. This is your actionable playbook. We've covered the heavy theory, the parallel teams, the sequential fixers, and the managers. Now, let's actually turn all of this into a highly practical, real-world deployment strategy. I highly recommend taking a mental screenshot of this cheat sheet. When you're sitting at your desk staring at a dataset, this matrix is your guide. Got noisy data and need to reduce variance? Deploy bagging or a random forest. If your data is actually relatively clean, but your models keep underfitting, AdaBoost attacks that bias directly. For almost any standard tabular data competition out there, gradient boosting is absolutely your go-to. If you're fighting for that final bleeding edge 1 to 2% of accuracy and you've got the compute budget to spare, build a stacking ensemble. And if you just need a really quick combination of diverse models, standard voting works wonders. Basically, you just match the tool to the specific error component you're trying to fix. Let's move to and see how this builds into a definitive 4-step order of operations for literally any tabular data problem in production. Step 1. Seriously, do not overthink it. Start with light GBM or XGBoost using their default parameters. Step 2. Tune your key hyperparameters, things like the number of estimators, the learning rate, and your max depth. Step 3. If, and literally only if, you need that absolute maximum performance, stack 3 to 5 highly diverse models together. And Step 4, the golden rule across this whole thing. Use cross-validation throughout the entire process so you don't accidentally fool yourself into thinking you have a great model when you've actually just overfit your data. I want to conclude this explainer by leaving you pondering a massive, ongoing tension in modern machine learning research. We constantly hear about the sheer world-eating power of deep learning and neural networks. Yet, as we've explored today, when it comes to standard tabular data, the rows and columns that make up the vast majority of actual enterprise data, XGBoost and gradient boosting models consistently outperform neural networks. Despite millions of dollars in research and incredible new architectures, neural networks just continually fail to decisively beat well-tuned ensemble decision trees on tabular data. Why is that? What is it about the specific structure of human-created data tables that makes this sequential correction of boosting so genuinely unbeatable? Think on that. Thanks so much for joining me on this explainer, and keep exploring.